we'll change the topic to something totally different. We'll go to what's called operators and focus mainly on the so-called backward shift operator B. So in general, an operator A is a function of a time series or stochastic process. So what happens when you apply an operator on a process is that on time series it yields a new time series. Same thing applies to a stochastic process. When you apply an operator on, say, xt, you get a new stochastic process. The most important operator for us in this course is the so-called backward shift operator. We call it B. In other textbooks it's called something different. It may be called sometimes, but we call it B for backward. So if you apply the backward shift operator on xt, what you get is xt minus 1. So it's just shifting time. And then obviously if you do it j times, you step backwards j times. All other operators that we will consider will be expressed using B, just so that you have kind of one nail to anchor everything to. So let's go for the easy one first. The forward shift operator is pretty much doing the opposite of the backward shift. Namely, if you apply it on xt, you get to xt plus 1. And if you do it j times, you get j steps forward in time. And then obviously, if you combine a step forward with a step backwards, well, then you get to the identity operator. You stay where you are. So the forward and backward shift operators are each other's inverse, which means rather than using the forward operator, we will use B inverse throughout this course. Another operator that we will use a lot is the different operator. So you've all done kind of applying a diff operator on a sequence of elements, and what you expect to get out is one element minus the previous element. That's the same thing here. It's xt minus 1. Now, if you want to do this operator-wise, well, we have an identity operator on the xt and a b on xt to get xt minus 1. So that we can have the operator polynomial 1 minus b applied on xt. That gives us the difference operator. So per definition, the delta here that we'll use for the difference operator is 1 minus b. Now, the next one is the so-called summation. And summation makes somewhat sense. It's a sum of all previous elements in the sequence on the time series. When you apply a summation on xt, you get xt plus xt minus 1 and so forth. And again, we can take, whenever it says xt minus something, we can take that minus something and pre-multiply b to that power. So b to xt, b squared on xt. And then we can combine and make an operator polynomial in front and leave xt out at the back here to get the infinite sequence of 1 plus powers of b here. If we look at the summation and compare with the difference, if we do the summation of xt, it's equal to xt plus the summation of all the previous ones. That's kind of obvious, but it helps us to look at if we first do the summation and then the difference, like it's written here. Well, that's the summation of xt minus the summation of xt minus 1. That's what come out of the difference operator. But now, as we just wrote up here, xt is equal to sxt is the xt plus sxt minus 1, which is also what we have to subtract. So we're left with xt. So they are each other's inverse. We proved it one way. If you do the other way around, first the difference and then the summation, well, we end up having the same thing. We have the infinite number of elements here, but we have to keep track of all the powers. And here we have an xt minus 1 here, which means we can change that, and we have a b here that we can multiply in everywhere to get to this down here. And what we notice is that, well, all the elements from here on and forward, they are identical and subtracted over here, so we're just left with xt. So indeed, they are the summation, and difference operators are each other's inverse. And we can write it like this: 1 over 1 minus b, or the infinite sum of powers of b, equals the summation. Now, if we look at the combined properties of all these different operators, one important thing is that they are all linear. So if you do a linear combination of an operator on a linear combination of two different time series, you can do the operator on each time series by itself and use the weights or whatever coefficients you have on top. That will work. And you can combine these operators into new operators. One classical example is the power series, where you have an infinite sequence of powers of set here. Well, if we then, instead of set, insert one of our operators up here, typically the backward shift operator, then we have an infinite sum here of some coefficients times the operator to some power, also going to infinity. That's something that we will be using quite a bit in the following lectures. Other examples of combined operators, well, we showed before by definition that the inverse of the difference operator is 1 divided by 1 minus b, as we have it over here. But we also learned from algebra earlier on that 1 over 1 minus z is equal to the infinite sum of z to the I power, from 0 to infinity. So that's basically what we're doing here is transparent and equivalent to what we do when we learned about infinite sums in an Introduction to Mathematics course. So we have these different ways of writing things, but we won't just restrict ourselves to work with infinite polynomials. We will also use finite polynomials. So you can have, say, a theta operator here with some argument here, where you have some parameters and then you have some powers of your argument here. One example could be, and that effectively the comparison to this up here, so meaning that whenever index I up here is greater, or in the previous slide, when index I is greater than q, the argument here, or the weight or parameter associated, is 0. So a typical example is the theta of b polynomial here, where you have 1 plus theta 1 times b plus and whatever number of elements that we specify up till we get to theta q, b to the q power. And we will often use theta 0 to be equal to 1, just because then we have defined things and we can then use the scaling. We'll get back to that by scaling the noise instead of scaling here. Otherwise we have two elements and we cannot estimate both. A little bit more complex structure is here. The Cauchy product of operators is the so-called discrete evolution. And basically what this means is that you have to, the product of lambda with psi to get pi, you have to make sure that you have the sum of all elements in the two things that you are convolving. That gives you the same sum of subscripts in the response. So to get 0, you can only have lambda 0 and psi 0. To get 1, you can have either lambda to be 1 or psi to be 1. And if you go to 2, well, you can have lambda to be 1 and psi to be 1 to get a sum of 2. You can have lambda to be 2 and psi to be 0, or lambda to be 0 and psi to be 2. So then you have 3 options. And then you just keep going. But effectively what you look at is that you always make sure that the sum of subscript equals what you want to get, the order. So it's basically just like multiplying polynomials together. And if you, to do it a little bit more, if you have 3 different operators here, using polynomials using the operator h, then if they fulfill the convolution here, if this is fulfilled at the multiplication here, then they satisfy the Cauchy product as given up here. So that's pretty much the definition, that if you look at the arguments here, the coefficients, and if you look at the operating polynomials, multiplying them together, that corresponds to doing it, to looking at the coefficients up here. That was what I wanted to say about operators for now. And finally, just a summary showing the highlights from what's been covered in the 3 different parts today. Just briefly, local trend models, what we're looking at here. There should also be something about exponential smoothing. We look at the iterative updates, and then we look at primarily what we're going to use is the backward shift operator and the different operator. So thanks. That was all for now. We will see you back in class soon, and then we can discuss anything that I did not explain well enough. So take care till we see each other.